This is IAT355 Visual Analytics, Lecture 6, Visual Perception, Part 2. In the previous round, we'd spoken about a simple model of pre-attentive processing, a simple model of perception, and how that can lead to pre-attentive processing. And in the next segment, we talked about the perceptual properties that we have, in particular how that relates to lightness and color. Today, we're going to be talking about nonlinear perception, which is the situation where you find most of our perceptual capabilities are not a direct correspondence one-to-one with the strength of the signal that we're perceiving. So we're going to talk about that concern and how to deal with it. And the last part of Visual Perception 2, Lecture 6, is going to be about integral versus separable visual items. So let's now talk about nonlinear perception. So nonlinear perception is the situation that most of our perceptual capabilities live in. Perception is not uniformly linear, and this is true of hearing, of vision, of taste, touch, smell, etc. Some things, however, we as people, most of us, get it pretty close to right. So we're, most of us, capable of judging length after a certain amount of practice that most of us have. So if you estimate something is about 1 meter long, you're likely to be right about that. You're likely to be right to guess that something's 2 meters long. There's a range that's acceptable there, probably below 1 millimeter, you can't really tell, and, above 1 or 2 or 300 meters, you probably can't directly perceive that so well. But within sort of the human scale range, we're good at perceiving length, and we're also good at perceiving temperature pretty close to what the real temperature is. You can guess temperature correctly. For other perceptual domains, we tend to underestimate. Certainly the domains we care about in the domain of visualization, we tend to see a signal and underestimate the strength of that signal. And we'll talk about what I mean by signal in a second. We are pretty good at telling, that there is a difference, but we might underestimate the ratio of those two differences. And I'll demonstrate that shortly. Our capability of sensing ratios is pretty good, and it's driven by the fact that what we're trying to do when we are seeing the world is we're also always automatically having to adjust ourselves to the strength of the signal or the strength of the impulse that's out there. So, for example, on a bright sunny day, your irises contract to let less light in, your retina adjust, etc., etc. When you go into the dark, your eyes adjust rapidly so that you can see what's going on in a darkened room or where there's not so much sunlight. If any of you have done any work with Zoom recently, you'll know that, unless you decide that you don't care about the appearance of the visuals, you're always having to adjust the camera to be able to deal with the proper amount of light that's actually present in the scene. Our eyes and the rest of our sensory system is doing that all the time automatically. And as a result of that, some things have to give. The ability to see something, hear something, taste something, that's important. Whether it matches up to a number, that's not so important. Okay, so why do we care about any of this? Well, visualization, the purpose of it is to turn numbers into pictures, right? We got a set of data and we want to plot the data on a line, or we want to set the size of the circle to be equal to or proportional to the size of the data value that's associated with. That's what we're trying to do. That's what visualization systems are built for. However, we are not depicting numbers that are then plugged directly into your mind. What we're doing is we're drawing pictures that are perceived by people just like us. And what our users must do is turn those pictures into numbers. And it's this turning pictures into numbers thing that's important to us, because that transformation process, that's what perception is. And if you're not aware of the fact that, that transformation is not identical to the one you're thinking of when you turn numbers into pictures, you can find yourself kind of misleading the user, and that's not what you want to do. So, as an example, here's a simple little example. Take these two circles and just imagine that the area of this circle is equal to 1. And what I'd like you to do is to guess the area of this circle. How much bigger by a factor is this big circle compared to the small one, where this area of this circle is 1. Okay, now that you've spent a moment thinking about it with me not talking, let me just show you what the actual areas are. And I've rescaled, once again, the areas to 1. So that's the area of this thing is 1, and the area of this thing is actually 20. And you may have guessed probably something on the order of maybe 15, 14, up to 18. Probably you didn't guess 20, unless you looked at the slides and measured them and all that kind of good stuff. But what's going on there is our ability to estimate area tends to underestimate the size of things. Particularly if I give you a scale, that I've set this size to be 1, and so therefore, what's the size of this in these units? It turns out it's 20. And our ability to see that is kind of, it just has its limits. We underestimate area. So Stevens, a number of years ago, in the early 1960s, was interested in this perceptual mismatch between linear functions and other functions, and he came up with what's called Stevens's power law. And the way it works is the sensation of a stimulus X, or the intensity of the attribute X, the sensation of that attribute is equal to some constant times that attribute to the power. Now, if b is equal to 1, that's really just ax, because b is x to the exponent 1 equals x. And so we see in this graph that length is linear. We're good at estimating length when we see the length of something. We can tell that something's 2 meters and something's 4 meters and so on and so forth. For taste, we overestimate. The value there is approximately 1.5. Heaviness, we overestimate. The exponent there is a little bit greater, and we really, really overestimate shock. Even small increments of shock, really, really get overestimated. They hurt like hell. And the reason why they're hurting like hell, of course, is that electrical impulses are directly plugging into our nervous system. On the other hand, we underestimate a bunch of things, in particular in the visualization space. So we underestimate area somewhat. We underestimate volume even more. We underestimate brightness even further, and loudness even further, and smell we really underestimate, which you could argue might be a good thing. Let's move on. So with respect to this experiment that he did in 1961, Stevens was interested in mapping out what the exponent is. And so the exponent for brightness is about 0.33. That is to say, it's the cube root, roughly. For smell, coffee, it's about 0.55, so square root roughly. Loudness, 0.6. But temperature, we're also pretty close to the mark. The exponents seem to be 1. For taste, it was 1.3. Saltiness was the stimulus there. Heaviness, 1.45. And electric shock, 3.5. That is, the cube of the voltage is what our feeling about it is. Now, we're not actually depicting shocks in visualization systems, thankfully, but what we are doing, of course, is we are sensing some of this stuff. So this comes into play. When you want to depict the area of something, you need to do something about it, or at least be aware as a consumer that something needs to be done about it. So, experimental results for B for length tended to be around 1, as we can show here, seen here, and for area somewhere between 0.6 and 0.9, for volume 0.5 to 0.8. And so the heuristic is B is roughly equal to 1 over the square root of the dimensionality, where dimensionality is 1, 2, or 3, square root of 2 for area, square root of 3 for volume. And so a suggestion to how to deal with this in the domain of visualization is, let's say you've got a set of areas that are just linear scales of areas according to the actual numbers that you want to depict. So let's say this circle in the left set here, this inner one is area 100, this one's 300, the next one's 600 and 1200. This 1200 circle is 12 times the area of the 100 circle. In order to counteract the effect of underestimating area, you should probably exaggerate the area of the circles that you're drawing so that you can get the point across. Now, there may be some reasons in which that's an unwise decision. If you're drawing a lot of circles, say on a map or something like that, each of the circles that you draw overdraws other circles, and so you might just have to accept that exaggerating area is not the right thing to do because of the other things that might go on in the display that are valuable to depicting the situation. But if you're interested in, counteracting the perceptual effects of underestimation of area, this is the kind of thing you might consider doing. Okay, so given that we've kind of documented through experimental evidence and possibly our own experience the fact that we tend to underestimate things, or more to the point, we estimate things incorrectly by when we look at them, it's probably a good idea to think about what is the most accurate and what is the least accurate way of depicting something visually. So it turns out that the most accurate stuff to visualize is position, typically on at its best on a common scale. So that is to say, let's say you've got an axis here. I'll just reuse this one here, which is an arrow pointing from most accurate to least accurate. Let's say there's a scale on here. If I were plotting points along this scale and I had tick marks on this scale that were numbered and so on and so forth, I would be very good at detecting the position along that scale, along a common scale. Less good at positions along a non-aligned scale. Let's say you have a skewed scale that looks like this or something like that instead of being rectilinear like that. So less good at that. Without an accompanying scale, we are pretty good at detecting length, but not as good as we would with a scale accompanying it. We're also reasonably skilled at detecting slope and angle. What is this angle, for example? We're reasonably good, we're very good at detecting 90-degree angles. That's approximately 90 degrees, and probably 45, but less skilled at other angles and, coming up with the number of degrees that an angle is used to, unless you're practiced at visually sensing angles. But it's in the same range of perceptual capabilities as length and temperature, but, we don't use visualization to depict temperature directly. We report the numbers. Further down here on this list, of course, is area, followed by volume, and lastly, color. Now, that does not mean we can't see color. What this means is that our ability to turn color into numbers is not as good as we would desire it to be. And that's one of the big warnings from this sequence of lectures is that, color is good for some things. We have a huge amount of experience of seeing colored objects every day, but if we want to turn colors into numbers, if you're wanting your user to do that, you're asking for trouble. Okay, so let me demonstrate. Can you put these in some particular order? So here's a bunch of random swatches, orange, green, a couple of purples, magenta, cyan. What's the order? Well, one of the problems with this is, of course, it's a trick question. Can you order these? Can you order these online? Well, here they are. But one of the big challenges is in order to make use of separate colors like this, you have to do something to tell the user what you're thinking as the depictor of color, as the person who is creating the visualization. So we'll talk about that in a bit. The punchline is, no, you can't. And the only way you can is if you really are constantly reminding the user what the deal is with respect to color. So there are a number of ways in which you can use color to help the user understand the scale of things and so on and so forth. And here are some examples. But this one here, the full spectral scale, is probably the one that is, in fact, the least useful. So over here on the left there's no hue. This is strictly black, white to black. You're in some sense using luminance there to depict a color value, but again, that's not necessarily going to translate well to numbers. And in these little color ramps, there's 5 values. You often see people wanting to use the full spectral scale because, people have in their mind, oh, well, there's numbers attached. I just pick off the wavelength, 400 to, 700 nanometers, translate that, add 54, and bam, Bob's your uncle, I've got a color scale that's accurate. But the problem is, our ability to sense color, as we showed in the CIE chromaticity diagram, is extraordinarily nonlinear. We're really good at seeing green and really good at seeing yellow things. But if you highlight something that just happens to fall in the yellow scale, you're putting a signal to say, look here, look at this yellow stuff. That's what your perceptual system's telling you. But what it's not doing is translating it into a number. In fact, what it's commonly doing is creating a fake feature for the user's eye to see. So one of the things that you can also do is instead is pick a kind of a family of hues and vary the lightness. Or if you needed a double-ended scale, pick two colors and vary the lightness / saturation. So where you do see this used is in things called a heat map. Commonly red and blue are used in order to get around the problem of a common form of color blindness, namely red-green color blindness. And so you do see red and blue used as opposite ends of a heat map. That's why it's called a heat map, red for hot, blue for cold. Which in turn is a metaphor for body temperature. And here in this thing, this is a stock market map from 2007, and you can see what color is being used to do is to depict the rise or fall of the stock price for this time period, and the colors are redundantly encoding something that the little piece of text here is also saying. So this is a drop of 3%, and that's an increase of, actually, that's an increase of 3%, and this is a decline by -4%. So interestingly, the negative values are red and the positive values are blue. They've also been very careful to do one thing here, and that is to have roughly the same visual magnitude here, -4 and +4, even though the negative value goes up to 4, the positive value only goes up to 3. The reason why this thing functions reasonably well is that the redundant use of numbers helps with the perception. So you do often see color used in, particularly in maps and in other types of applications in visualization. And one of the things that can be a concern, not only do we have this problem with the perception of color, we also have a problem with the reproduction of color. I have, in fact, 2 monitors on my desk here, and they're the same brand, made by the same people, possibly manufactured by different manufacturers, and their actual color performance is different. I have a favorite monitor I keep that I put most of the stuff that I do anything to do with color in, because I don't like the color reproduction on the other one. So this thing, ColorBrewer, is a system put together by Cynthia Brewer, and hence the name. And what she has done has built a system that enables you to preview color ramps. So let me just go to that now. So this is a live demo now, theoretically. Please hold. I need to go there. Just 1 second. I need to navigate to the proper spot. There we go. And so what you can do is pick color ramps. Right? So there's a red one, a blue one. And what this does is uses the counties of the southeastern United States, that's Florida down here, Georgia, Alabama, etc., and draws a color ramp from the highest value, the lightest value, down to the darkest value. And you can control the number of classes that it is going to draw. So let's just do that. Let's do 7 now. And what it does is draws these kind of color swatches, has these intervening values. It shows you a tooltip so that you can see what the color HSB, hexadecimal, etc., is, all the color specifications you'd want. And it does a number of other interesting things too. First, it indicates whether or not this thing is suitable for folks with who are colorblind. And so this one seems to be okay for that. It suggests whether or not this thing is photocopy friendly. There's a tooltip that's popping up here that says 7 class purple to blue is not photocopy friendly. And that's a picture of a photocopier crossed out. So if you were to photocopy it, print this thing out in color, take a photocopy of it, probably wouldn't work. You'd end up with, most of this stuff being closer to black or something like that. So it also talks about using LCDs, using printers, and other types of things. So this thing is serving two broad purposes. One is the capability of perception, and the other thing is whether it's going to be print friendly, photocopy friendly, and friendly for various displays. Back in the day when she first introduced this thing, it also talked about CRTs, but that's less of an issue. You know, nobody cares about CDs no more, CRTs anymore. You know, they're too big and they take up space and they consume power, so get rid of them. So if you are going to use particular color ramps, going to this site is a great thing to do because it gives you the opportunity to test out whether your color choices are going to work. She has a whole bunch of pre-baked ones here, and she also does double-ended ones. So these are diverging colors now. So white in the middle, and then negative values and positive values. So this is a 7-spot color ramp, and the things that we're showing here are the two hues, the brownish yellowish hue and the greenish hue, and they're readily distinguishable from each other. Okay, so that's ColorBrewer. Let's go back to the slides. That's available at colorbrewer2.org. Sorry, that's cut off a little. But the basic idea is that you can go to this site. It's free, you know, and the original version ran Flash, you know, which has become obsolete. So, you know, this is a JavaScript version or something. Cool. All right, so let's move on. One of the things you always have to watch out for is the visual context. And, you know, I've sort of pointed that out a few times. Here's a great example of that. Let's just concentrate on what the colors are. So we have a little bit of a grayscale going on here, right? White to darker colors down to black, and the 6 sort of canonical colors, red, green, blue, you know, orange, and magenta. So do you think that this color is the same as that? Well, it turns out, keep your eyes on them, they are. So the actual RGB, if you were to put a ink drop, you know, a color picker, tell me what color this is to this image, what you'll get is that the RGB value of this is pretty much equal to the color RGB value of that. Going back again, oops, too far. They are actually the same color. And so that's another, just a general concern about the way in which our visual system not only responds to the actual light that's flowing into the scene. We have a model of what light is like and how it works in the real world. That's just automatic. We don't have to think about it. And we know that this is black, even though the actual RGB value of this and the actual RGB value of that is identical. And we know that because we can say, oh, this guy's put a couple of color swatches on his deck, and over here it's in the shade, and over here it's in sunlight. We automatically adjust for that, and we instantly, without thinking about it, perceive these two things. That is black, and we perceive that somewhat darker color also is black simultaneously, even though the values are different. So those kinds of perceptual concerns are always present whenever we're doing visualization. So it's something always to watch out for. So what that does is serve as a warning that using color as a mechanism to try to do depictions of things is something that's, well, not dangerous, but it's just not going to be as effective at depicting numbers in the way you would like to. So you can use color for doing things like calling attention to specific data, increasing appeal, memorability, and representing discrete categories. In the previous slide set, in the lecture 5.2, we talked about Colin Ware's set of colors, you know, red, green, blue, yellow, black, white, etc. It's good for that, particularly if you have control over the display, you know, as you would typically in most analyst sessions. The other thing is less is more. Don't use too much color, and in particular, don't use blues too much. And use adjacent colors if you're going to have to, if you want to distinguish those two things, vary them in hue and value, not just hue, or not just value for that matter. For large regions, don't use highly saturated colors. In fact, really stay away from saturated colors. You probably know from playing with Tableau for a while that the entire color vocabulary that they have, you would label pastel. It's very, very subtle, and it's very subtle for a reason. They had a professional color expert design those colors. Her name's Maureen Stone. She's been an adjunct prof here at CIAT. And, you know, she's been working in color for 30 years, and, you know, she really knows what she's doing. And she designed and redesigned those colors to be really perceptually different from each other and not in your face. So watch out and try to avoid the temptation to overdo it with color. Don't use high saturation, spectrally extreme colors together, particularly red on top of green or green on top of red. Because what happens when you do that is that your ability to perceive red, because it's a completely, you know, the opposite perceivable wavelength to blue, your eye is adjusting in some sense to that color, and blue just turns out to refract differently through your glasses and through your eye, and so it appears as if one is floating on top of the other, which is not what you want typically. So using color for grouping, for search, and things like that, that makes some sense. Finally, just to talk briefly, very briefly, about texture, our ability to perceive texture, you sometimes see texture used to, you know, put a texture, diagonal stripes or something like that on glyphs or other markings in the scene. You don't see them used too commonly unless essentially you're out of other visual resources to use. We're capable of telling the orientation of, say, stripes or a checkerboard pattern, but it's a very complex attribute to analyze, and you don't see it used much in modern visualization tools. It's really good for certain things. If you have a surface texture on a curved surface, it's really good at enabling you to perceive the curvature of that surface, which is why you see texture mapping in 3D video games and all that kind of stuff. But to use it as a kind of a visual data variable, probably not so good. Okay, so that wraps up Lecture 6.1, which has been about nonlinear perception. So we'll stop there.